use for development of the supervisory control field. So we gave this very brief introduction to the automata. And basically, an automaton A has been defined as a four tuple made of a set of states, a set of events, an initial state, and a transition function. That's our definition, and based on this, we can define also a graphical representation of automata, which is totally equivalent to this one. And in particular, for example, we have an automaton like this. So we usually represent states with circles. And transition function elements are presented through arcs labeled with some label. Okay. And these states belong to the set of states QA. Labels belong to the alphabet sigma E. A state with an arrow without any predecessor state identifies the initial state, and that's it. Then you can go on with other states and so on. Okay. You may have also something like this. We defined this as a possible automaton, it's a regular automaton, but this state has a particularity. So this state is not reachable from the initial state. Based on this, we give a formal definition, which is quite straightforward. So states can be reachable or not reachable. And meaning that a state is reachable if it is reachable from the initial state. It seems kind of tautology, but it's not this. And states which are not reachable are meaningless because they do not contribute to the evolution of the automaton. Actually, the evolution of the automaton is described by the concatenation of events that for us are labeled, okay, concatenation of labels or concatenation of events that are executed during the evolution of the automaton. We called this set of evolutions as language. So the language of an automaton is defined as the set of executable strings of the automaton. A string is any concatenation of events executed by the automaton. So in this case, in this example, the language of this automaton is made of epsilon, which means the null string, which represents no events. Okay? It means that you start from the initial state Q0 and you do not move. You stay there. Conventionally, we represent the fact that you don't move with the execution of a null string. Or you can go on, in this case you can execute alpha, that's a string with length equal to 1. Or you can do two steps, so you execute two events in sequence. First alpha, and then you have a choice between beta and delta. So another string is beta, alpha, beta, and alpha, delta. And then that's it. Okay? So from Q4 you could execute alpha, but Q4 is not reachable. So Q4 does not contribute to the language. Okay, so that's it. In particular, Q2 and Q3 are also called the deadlock, in the sense that once you reach this state, you cannot move anymore. So these are deadlocks. In general, we do not like deadlocks, but that depends on the specification. Okay, so in general, deadlock means that you are there and you don't get out of the state. Okay, so I think we didn't define the pseudo-automaton relation.
Just a question.
Yes,
You can have alpha from two different states arriving at two different from two different initial states arriving at two different final states, like that.
I didn't understand very well, but in this example, there is only one initial state, which is the one pointed by this arrow. So that's the only initial state that we have.
Okay. My question is this: you can have, let's say, from Q0 apply alpha and get to Q1, and then from Q4 apply alpha and get to something else. That's possible.
So it's possible if you start from Q4, if you apply alpha, you go to Q3. That's
A different state.
possible.
Oh yeah, that's good. If you're a different position, you say move right. It will.
Yes,
Okay.
correct,
Understood.
correct. So this question gives me the chance to make another comment. So we have two arcs labeled with alpha. So don't care about the fact that Q4 is not reachable. So we have two different events associated. We have the same event associated to two different transitions. Okay, this is a transition between Q0 and Q1, and this is between Q4 and Q3. That's totally legal. This is not a problem. Okay. So this is also legal. Let me do this Q5, and let me label this with alpha. This is also legal. Okay, and the meaning is if you start from Q0, you first have to execute alpha, and then you may also execute alpha again. You execute this event twice. Okay, this is absolutely legal. And of course, let me just make another example. Alpha, and alpha. These are two different automata. Okay, because this is able to execute alpha just once, and this can execute alpha twice. Okay, so these are completely different automata. This is one event, this is two events. Okay, alpha can be any operation in a manufacturing system. So can be bring this paper out of the door. Okay, and I may want to bring many papers here on the table out of the door. Okay, so this is simply a way of counting how many times I do an operation. So this is totally legal. What is not legal for us is this one, alpha. Because this is a non-deterministic automaton. So we start with deterministic automata, and this is prohibited because if you start from the initial state and you execute alpha, you do not know what is the next state. You may associate a probability, so this non-deterministic automaton may transform into a stochastic automaton, but this is not our goal now. Okay, so this is the only thing that is prohibited for our automaton. Okay, other comments? So last time we also said that we can also remove states like Q4 since they are not reachable from the initial state. So I can remove it. Of course, if I remove this state, this arc has no more any meaning, so I must remove it. That's clear. This does not affect anything related to the state Q3. Okay, let's see. When I remove unreachable state, I'm obtaining a new automaton, that is called accessible automaton. So an accessible automaton is made only of reachable states. Okay? Accessible automaton is just an automaton made of reachable states. And we don't define it formally because it's clear enough. We can define the function based on this definition. A function which has an argument, which is an automaton, and gives us back another automaton, which is the accessible part of this automaton. This corresponds to the operation that I showed you graphically now. So I give you the original automaton. The act of removing unreachable states along with the necessary acts means to perform the accessible, to compute the accessible part of the original automaton. And we write exactly like this, AC of A, AC of the automaton A. So we have an automaton A, we apply a function which extracts the accessible part, extracts another automaton which is made only of reachable states. Okay? And the idea is exactly the idea that we have seen there. So the language of A is equal to the language of the accessible part of the automaton A. So the function accessibility does not change the language of an automaton. This is the goal, our goal. So we can remove unreachable states without changing the language. Okay? So sometimes I can forget to tell this in the future, but unreachable states are never useful. So we must remove them as soon as we realize that they are not these states. Okay. Any other comments or questions related to this? So let me make a second example. Okay. I want to make a second example. Okay, let's remove also. So the second example is this one. I give you this automaton, let's call it A. Please write it formally as a tuple. Okay? Don't do that analytically, because I will give you only 5 to 6 seconds. So try to imagine to define this automaton formally. Okay, so time elapsed. You're lazy, huh? So let's move on. What is the set QA? Is the set made of Q0, Q1, Q2, Q3, Q5. Okay. What's the initial state? Q0. What's the transition function? Transition function is the set of all the arcs that we see here. So first element from Q0 to Q1 with the label alpha. Remember, we can write like this, but we don't do it. Q0 alpha, Q1, that's the first arc. And then we have the second arc, third arc, fourth arc. So we have 4 elements here. Okay? Can you write the alphabet also? Can you tell me the alphabet? So sigma 8, I will write. What is sigma 8? Is the set of events, so the labels. What is sigma 8? Alpha, beta, delta. Okay. Are you sure? How many of you are sure about this? How many are not sure? How many are sleeping? So should I write twice alpha? No, because this is a standard set. Okay. But I say that this is a possible solution, but this is not necessarily true. This also could be an event. Sorry, an alphabet. For example, this one. I added another event called pi in this example. Is it legal to have another event here which does not label any mark in the automaton? Does this violate any definition that we gave about automata? No, this does not violate any definition. So this is also a possibility. Okay? So the alphabet may contain events that are not executed by the automaton. That has a special meaning. That is totally different from having a state which is not reachable. Having a state which is not reachable is equally to have nothing, because this state will never be come across. Okay? But in this case, it's totally important because we give events a lot of information, a lot of importance. We associate input and output to events, so events are important. And so this has a special meaning for us. This means that the automaton is able to recognize the event pi, but the event pi does not make any transition in the automaton. Okay, that's extremely important. Okay. The fact that you have an event set here does not mean that all these events should be necessarily executed from any state. So you recognize beta, but from the initial state you don't execute beta. So what's the meaning? The meaning is that when you are in Q0, the automaton recognizes very well the meaning of beta. Beta maybe is open the door. But the automaton does not execute beta from the initial state. Okay, and the same for delta. So the fact that you have events here does not mean that you have to execute necessarily from every single state. So from this state, you don't execute beta, you don't execute delta, and you don't execute pi as well. Okay, and pi happens to be not executed from any state, so it's just a particular case. Okay. We will see this fact later with the following definitions. So having or not an event is of extreme importance for us, because the automaton may recognize or not a symbol. Okay. So it can be a robot, this can be a robot model, and this can be the commands that is able to understand. Maybe I program the robot to open and close the door. And if I program him to open and close the door, I cannot ask him to close the window, for example, okay? Because he is not able to do so, because it's not programmed to do so. And in this case, it means that the robot is not able to recognize the command. On the contrary, I may program a command, for example, close the window, But in a particular instance, I may decide to never execute this command. Okay? So these are two completely different views. Okay, so I think this is clear enough. So let us introduce a relationship, which is the subautomaton relationship. The subautomaton relationship is represented with the symbol less or equal. Okay, so we write like this, and we say that A is the subautomaton of B. And it means that given the two automata, so it means A, which is equal to QA, sigma A, IA, delta A, and given B, which is QB, sigma B, QB, and delta B, we say that A is the subautomaton of B, if and only if, it's a definition, the following four conditions hold. QA subset of QB, sigma A equal to sigma B, IA equal to IB, and finally delta A subset of delta B. Okay? So these are the four conditions that define the subautomaton relation. Okay? What's the practical meaning? Practical meaning is very, very easy because we see that A is subautomaton of B if it has the same initial state, the same labels, that's easy, and a little less states and a little less arms. Okay? So basically, it's very simple. We can obtain a subautomaton starting from an automaton, just removing some states and removing some arms. Okay? So basically what we did before with the accessible function was the extraction of a subautomaton of a given automaton. So we were given an automaton A, and the accessible function basically extracts a subautomaton, because what we did was only to remove some states and remove some args. What remains is, by definition, a subautomaton. We didn't touch the initial state and we didn't touch the set of events. The set of events, you see again, it's of paramount importance. So we don't have the right to touch the set of executable events. Okay, these are extremely important. That's the definition of subautomaton. Let's see some properties. They are very so. So the first one is that the relation is a reflexive relation. What's the meaning of reflexive relations? It means that A is in relationship with itself. Okay. So basically, A is a subautomaton of itself, because it means that you take the equal here and here. That's it. Okay. And most importantly, it's transitive. what's the meaning of transitive relation? It means that if A is in relationship with B and B is in relationship with C, then A is in relationship with C. Okay? So we translate this in our formula. So A subautomaton of B and B subautomaton of C, this implies A subautomaton of C. Okay? We don't prove it because it's trivial. It means that if you obtain A removing some states and arcs from B, and you obtain B removing some states and arcs from C, then you can obtain A from C removing a little bit more arcs and states. That's it. But this is of paramount importance. We will use it many times. Okay? So the relationship of subautomaton paves the way to the definition of equality between automata. We can claim that an automaton is equal to another one. Okay? There are two definitions actually of equality between automata. One is based on the language. We know that automata are here just because they generate a language. So when they evolve, they generate a language. And the language is just the total description of the life of this automaton. So that's the important part of us. So two automata can be equal because they generate the same language. But it's quite clear that I could generate the same language with the two different automata, okay, with different set of states and so on. It's quite trivial to obtain this. So we define also a more structural, a stronger property, which we call strong equality or structural equality or isomorphism, when we want that the two automata are totally equal, structurally equal. And so we define language equivalence. Actually, we never use this one. It's not so important for us. And we say that A is language equivalent to B, if and only if. Language of A is equal to language of B, and again, sigma A equal to sigma B. On the contrary, we say structural or strong equivalence in this case. A is equal to B if and only if A is subautomaton of B and B is subautomaton of A. Okay? This is also called isomorphism. This is called isomorphism because this comes from ancient Greek language. It means the same form, the same shape. Okay, so if you draw the automata, you obtain exactly the same form. Okay, so actually, what's the meaning of this? So A subautomaton of B is exactly the definition. If you swap A with B, you obtain B subautomaton of A. So it means QA should be subautomaton, subset of B, but QB should be a subset of QA, so it means QA equal to QB. These are already equal, and here the same. Delta A contained in delta B, but also delta B contained in delta A, so delta A equal to delta B. Okay? So two automata which are structurally equivalent means that QA equal to QB, sigma A equal to sigma B, IA equal to IB, and delta A equal to delta B. So they are totally equivalent. Total equivalent. The four tuple is totally the same. Okay, that's the strong equivalence or isomorphism that we are interested in. Okay, is it clear to everybody? In reality, the real definition of subautomaton is slightly more general than this one. That's the clear meaning. That's easy to understand for everybody. But actually, to tell the truth, we said that the string defining the name of the states is not important. Okay? So we can have an automaton starting from state Q0, executing alpha, going to Q1. But we can also have another automaton, we can call it Q11, and this can be called Q2. For us, it's the same automaton, basically. I'm changing the name of the states, but what is important is the sequence of events it executes. Okay? So the name of the states is not important in this case. While this condition says exactly that the name should be corresponding strictly. So QA should be a subset of QB. Okay? And on the contrary, let me make this example. This is alpha, this is beta, 0, 1, 2. I can easily obtain a subautomaton as an example, just removing one state. For example, I can remove Q2. So I have Q0 and then Q1, and this is alpha. So clearly, if this is A and this is B, it's true that A is subautomaton of B. Okay? Because I just removed one state and one half. Okay? But I would like to extend the definition also if I change the name. Maybe this is Q11 and this is Q20. I want to say that if this is automaton C, also C is a subautomaton of B. Just changing the name. Okay? So the real definition of subautomaton is given also in this case. And the only thing we should do is to define a mapping between the names of the automaton A and the names of the automaton B. Okay? So we should define an injective function between the set of names, the set of states of A and the set of states of B. Okay? So instead of saying that it's like this, we should say that there exists an injective function. Injective function from F, let me say, from QA to QB, so that for every set of names in A corresponds a name in B. So delta A IACS as an image which is exactly delta B IBS 3S. Okay, so that's the definition of the injective function, which guarantees that there is a correspondence between the names. Okay, it's an injective function in the sense that QB may have more states which do not correspond to anything from QA. Okay, so injective means that some elements in the codomain are not image of any element from the domain. Okay, but if you pick one element in the domain, you have only one image in the codomain, which is an image of just one element in the domain. Okay, so two elements here have a map here in two different elements. That's the meaning of the definition of injective function. This is nothing more than a vocabulary between the names of A and the names of B. Okay? So that's the main idea. So we will go on with this definition. So in the future, when we will talk about equality between automata, we will take care of the fact that names can be different, names of states can be different. Okay, provided that there is an injective function between the names. Okay? So this injective function associates Q11 to Q0 and Q20 to Q1. That's it. Okay. So in the future, we will never define this function. So it's so easy that we will never go in such a detail. Okay. Now we introduce the first operation with automaton. So subautomaton is a relation because the result is yes or no. Now we define an operation. So the result is not a Boolean yes or no. The result is something else. In this case, the operation that we define is a function with two arguments, which are automata, and the result is still an automaton. So suppose that you are given automaton A and automaton B with the definition QB, sigma B, IB, delta B. Then we define the synchronous composition. Synchronous composition is represented graphically by two vertical bars, A synchronous B, and the definition is that the result is still an automaton. Okay? Still an automaton means the result is a fourth tuple again. Okay? So it is made of a set of states, set of events, initial state, transition function. Okay? So in order to define the synchronous composition, you have to define these four elements. Synchronous composition. That's an operation. Okay. So that's the definition. The set of states of the synchronous composition is the Cartesian product between the two operands. So Cartesian product between the states of QA and QB. So QA, Cartesian, QB. Second element should be an event set. So the alphabet of the Cartesian product is just the union of the two alphabets. So sigma A union sigma B.
Because of synchronous composition with the name of the operation.
Name of
The operation?
Yes, yes. That's the symbol of the synchronous composition. We just read A synchronous B. So that's part of the definition. Initial state. What could be the initial state? So it is defined like this. So it's a particular element of this set. So it will be a couple, because this is made of couples. So a couple of the initial states. So very easy. So IA and IB. And then the delta function, let me write it like this, delta A synchronous B, because this is the most complicated part. Okay, so now I need some space to define it formally. Okay. That's more the most intriguing part of the definition. The first three are trivial. So this delta function, delta A synchronous B, applies to what? You remember, the delta function is a function which goes from a domain which is made by the Cartesian product between set of states and set of events, and takes element from the set of states, which is this one. So it's quite complicated. So what is the argument of the delta function? The argument is a couple made by state and event. You understand that? So a state is a generic QA, QB. Okay, this is the state of the first element, comma, sigma. Let's write like this, that's it. Okay, that's the generic element of the delta function. And what is the result? The result is again a state of this automaton. So the result will be made of a couple of states of the original operands, of the original automata A and B. You understand that? We have a few cases depending on the fact that sigma belongs to which of the two alphabets. So sigma here belongs to the alphabet, so belongs to sigma A union sigma B. Okay. But it may happen that small sigma belongs exactly to the intersection between sigma A and sigma B. So it can be a common event between the two automata. In this case, I expect here to find the result, which is a state of the synchronous composition, so a couple of states. In this case, I have delta A QA sigma, comma, delta B QB sigma. You understand the notation? It's straightforward. I'm not adding any detail. Okay? So the result of the composition is a couple of states which are the image of QA and QB respectively from automaton A and from automaton B. When you apply sigma, the event sigma, starting from QA in A or starting from QB in automaton B. Okay? But it may be the case that sigma belongs only to sigma A and does not belong to sigma B. Okay, so it belongs to the different set between sigma A and sigma B. So this means it belongs only to sigma A but not to sigma B. Okay, so this event, small sigma, taken from here, may happen to belong to this part but not to this part. Okay, in this case, we can transit, we can make a transition only in this automaton, because this automaton by definition does not recognize sigma, so you cannot do that. And so the image of QA QB here will be delta A QA sigma. And for QB you cannot move, you have to stay there. Simply because it's impossible to move. Okay? Because small sigma does not belong to the alphabet of B. Dually, okay, you can exchange A and B, so sigma may belong to sigma B, capital sigma B, but not to capital sigma A. And in this case, since the alphabet of the first automaton A does not recognize sigma, QA cannot change, cannot transit. And so we will have QA, no delta function here. And here we will have delta B QB sigma. Okay, that's the definition of synchronous composition. Now we may want to understand why the inventors of this operation choose the name synchronous composition. So composition means to combine two automata to obtain another automaton. But why synchronous? Synchronous refers exactly to the first row in that kind of table. Okay? Basically, it means that if an event is recognized by the two automata, so belongs to the alphabet of both automaton A and B, then this event is accepted by the synchronous composition and corresponds to make a transition both in the first automaton and in the second automaton. Okay? So if you have an automaton A and B here, and you have sigma event labeling an out of QA and QB, the synchronous composition accepts the same event sigma, making the two automata change state at the same time, so synchronously. So the event sigma in this case is accepted synchronously by the two automata. Okay, is accepted by the synchronous composition when both automata accept this. Okay, that's the definition. On the contrary, we have these two strange cases when an event is recognized by the two, by only one of the two automata. And the definition basically says that the other automaton is totally indifferent to this event. So the event sigma belonging to just one alphabet does not create any problem to the second automaton B. So simply you stay there, but the event sigma is accepted by the synchronous composition. It's not refused. This is accepted, and this corresponds to making a move just one step in the first automaton. The second automaton does not move because it cannot. So we can imagine that when we try to combine the two automaton A and B, suppose that we are in the first case, when we try to combine them, we obtain another automaton which corresponds to a synchronous move, so the synchronous behavior of A and B. Okay? With the exception of these strange events that are accepted only by one automaton. Okay? Let's make an illustrative example. Okay. So we are given the two automata A and B, and what we want to do now is the computation of A synchronous B. Okay. I will give you 5 seconds again just to figure out what will be the result. Just to figure out what will be the result. So, my question is now this. Can you imagine if I give you enough time to be able to find a solution? I give you 10 minutes to find a solution. Who imagines to find a solution based on the definition? You're very humble. So who imagines not to be able to find a solution? You think it's impossible to find a solution? Actually, it's impossible to find a solution. Why? Why I cannot find the solution of A synchronous B now? So 10-15 minutes ago we made an example related to this question. So why it's impossible to find to make this computation? It's not the main issue. It's not. This should be necessary, probably quality, but now we are not doing this.
Because the transition function can take 3 values.
Generic sentence, I don't know how to correlate this with the original problem. It's related to the transition function. The problem, the hidden problem is related to this function. But specifically why?
Transition function of A is not subset.
Sorry?
Transition function of A is not a subset of B.
No, it's not this problem. Because here I have to evaluate these 3 conditions. Okay? So I don't know, I cannot answer this part here if I don't give you the alphabets of A and B. And we just made an example, and we can have the automaton A made of 3 events, alpha, beta, and delta. But delta does not label any alpha. But this changed the application of the definition. You understand? So in one case, for example, if delta belongs to the alphabet of A, when you consider delta here, you are in this case. On the contrary, if delta does not belong to the alphabet of A, then when you consider delta, you are in this case. So it's totally different. So I cannot give you graphically the automata 100%. I have to give you explicitly also the alphabet. So the alphabet is not necessarily just the collection of events that you see on the graph. It's not this. Okay? So, in order to answer, I have to write explicitly sigma A equal to something and sigma B equal to something. So suppose that we stay with this alpha and beta, and then sigma B equal to alpha and delta, the most, let me say, natural choice. But then we will change this definition and see what is the impact. Okay? So that's the paramount important point. So, for the first time, we apply the definition strictly. Then, from the second time, we will develop a much faster method. So, technically speaking, the states here are made by a couple of states of A and B. So, I should build all the possible couple of states. So, I should have, for example, Q0, Q3, Q0, Q4, Q0, Q4, and then Q0, Q5. Then I can have Q1, Q3, then Q1, Q4, and finally Q1, Q5. Last row is Q2, Q3, Q2, Q4, and finally Q2, Q5. Okay, I should put the brackets everywhere, but so again, sometimes we are lazy. Okay, so I'm starting from 3 states here, 3 states there, and when I do the Cartesian product, I obtain 9 states. Okay, so these are the 9 states belonging to A Cartesian B. A synchronous B. Okay, that's clear.
Why there is a point?
Because I'm lazy, instead of making the circle, I make the point. It's an alternative representation of automata. So sometimes we make the circle. I can do like this. No, I don't have enough space. I will not do it. It's too late now. So I do just the point. Okay, so this is first part of the definition. So we have here QA sync Cartesian QB. Then alphabet. Well, the alphabet I write it here. It's straightforward. A synchronous B as an alphabet, which is the union of the 2 alphabets. And so alpha, beta, and delta. It's very simple. Okay. Then the initial state. Well, the initial state is the couple of the 2 initial states. Here I have Q0, Q3, and so that's the initial state. Okay. And now we have to define the transition function, which is the most difficult part. Okay. In order to do so, what should I do? I should apply the definition which says, please start from any state QA, QB. So we have to repeat this procedure 9 times. Okay, and for any state, you have to try to couple it with all the elements of the alphabet. So with sigma equal to alpha, sigma equal to beta, sigma equal to delta. Then look at in which case you are, and then apply the formula. Okay. So let's start from Q0, Q3. It's a long procedure, this one. Okay. And then I should ask, do I have to label any arc from this state with alpha? So there is a transition labeled with alpha stemming or starting from this state. I have to apply the definition. So alpha belongs to both alphabets, and then if I'm able to find delta A and delta B, then I have a transition. So in order to answer this question, do I have, so that's the question, do I have a delta function in my result in the sequence composition starting from Q0, Q3 and alpha? That's the question. Do I have it? And where do I go? That's the question I'm trying to solve, the first question. So I go here from Q0, because here it's written Q0. I'm labeling an arc labeled with alpha, and I go to Q1. In B, I go from Q3 to Q4. So actually, the result will be decoupled Q1, Q4. Okay? Q1, Q4 is here, so I put an arrow here labeled with alpha. That's the first event for the first state. Okay? Second question, I rotate on the event. And then I put here beta, second event. So I keep the state, and then I go to beta. Okay. Where am I in this case? First, second, or third case? Third case. Okay, because beta belongs only to sigma B. Second cases. Beta belongs only to sigma A, but not to sigma B. So we are here. Okay. So please write the solution. That's the solution. We cannot find it. Okay, we cannot find it because this function does not exist. This value does not exist. Delta A Q0 beta does not exist. Okay, so since in this couple one of the two elements does not exist, I cannot write. So the answer is no. The synchronous composition is not able to execute beta from the initial state. Okay? Then let's move to gamma. Now, what is it? Delta. Can you find the image of this Q0, Q3? No, for the same reason. Okay? So, I used all the events, alpha, beta, and delta, starting from the first state. So for the first state, I've done everything. Let's now move to the second state, and then I should repeat. Can I label an arc with alpha and beta and delta and blah blah blah? Let me go a little bit faster. So I'm here, Q0, Q4. So you can have yourself like this, so you are in Q0 and Q4. You somehow highlight these two states. It's easier to follow the definition. So should I label an arc from Q0 to Q4 with alpha? No, because of this. This does not recognize, does not execute alpha. Can I label an arc with beta? No, this for sure no, because it's not in the alphabet. This is in the alphabet, but does not label any arc. Should I do it for delta? Yes, I can do it for delta because delta is not in the alphabet, so we are in this case here. Delta is not in the alphabet, so no problem about delta. QA will not transit. But the second state QB will transit with delta. So it means that when I can execute delta, and I will go in this state. Okay, this will not transit. Okay, I start from QA and I stay with QA. But with QB I transit, so I move this one. Okay, QA does not transit, but QB transit. So I will go to Q0. Sorry, this is fine. Okay, from Q0 to Q5. Q0, Q4. Sorry. No, sorry, I made a mistake. Sorry, I made a mistake because this is a simplification of the algorithm. I just applied the simplified version, but this is not what I said before. So let's go more straightforward to Q0. No, it's correct. Sorry. No, sorry, it's correct. From Q0 to Q4, I go to Q0 to 5. So like this. With delta. Okay, and that ends the events from the second state. Let's go to the last state of the first row. Let me say Q0, Q5. Should I label an arc stemming from Q0 to 5 with the label alpha? No. Beta? No. Delta? No. So this is a deadlock, so I cannot start with alpha and delta. And for beta, I cannot do anything because I don't label anything with beta. So that's okay also for the last state of the first row. Let's go to Q1, Q3. Q1, Q3. Can I move from here with alpha? No, because there is no arc labeled with alpha. Okay. Can I label an arc with beta? Yes, I can, because I label here. And beta does not belong to here, so I go to Q3, Q2. Q3, so this way, beta. And finally, from here, can I label something with delta? No. Okay, so this is done also for this one. Let's go to the next one. Q1, Q4. So from Q1, Q4, can I apply alpha? No. Can I apply beta? Yes, I go to Q2, Q4. So I go here with beta. Can I apply delta? Yes, I go to Q1, Q5. And then finally, for the second row, we are in Q1, Q5. Q1, Q5. So alpha and delta cannot be applied by definition. Maybe I can apply beta, and that's correct. I go to Q2, Q5. So here I apply beta. Finally, let's go to the last three, Q2, Q3. So we are here, Q2, Q3. I cannot apply alpha and beta by definition. and I cannot apply delta, so that's it. Let's move to Q2, Q4, this one. Q2, Q4, I cannot apply this alpha and beta, but I can apply delta. In this case, I will go to Q2, Q5, this one with delta, and that's it. And finally, the last one, Q2, Q5, it's really a deadlock, so I stop. Okay? So, that's the application, straightforward application of the definition. It's quite a long process. We will simplify it in the future because we simply observe that there are some unreachable states. Okay? So the synchronous composition quite often generates unreachable states. Okay? So the most straightforward application of the definition is just to follow execution. It is as if these two automata represent two guys that want to go to the same restaurant together. Okay, and so this guy is alpha is, for example, going to a pizzeria. Okay. And so this guy recognized the pizza and also liked pizza because in some states, I don't know, maybe on Friday nights, he likes to go to pizza. Okay? And this guy also recognized pizza. But from this state, it happens that this guy wants to go to pizza and this guy knows pizza but does not want to go. Okay? Maybe because he doesn't want to go to consecutive times or something like this. Okay? So we both understand what is a pizzeria. One wants to go and the other does not want. So what is the common, the synchronous behavior? The synchronous behavior is that we do not go to a pizzeria. Okay? On the contrary, suppose that we are here. Okay? We are in the initial state, we decide to go to a pizzeria, and we change our state. It means we accept to go to the pizzeria. Okay? But then here we have two different states. Here is, I don't know, shabu shabu, and this is yakiniku. Two different Japanese restaurants. Okay? What happens is that the shabu shabu is not recognized by the second automata, which means that I'm totally unaware of what is shabu shabu. The result of the synchronous composition is that I don't prohibit you to go to the shabu shabu restaurant. Okay? So if we are here, I say, I would like to go to a pizzeria. And he says, I would like to go to a shabu shabu. Okay, the result is that we go to the shabu shabu because this automaton is not able to inhibit this transition. Okay, so the common behavior is that we go to the shabu shabu. So let's try. Okay, so that's the final result. Completely different thing happens if the second automaton knows shabu shabu. What's the meaning of knowing an event? It means having this event in the alphabet. Okay? So in order to explain this difference, let's make the change. Let's make this change. Let's put beta in this event. That's the change I'm doing now. I'm introducing beta here. You don't see beta here, okay? But beta is in the alphabet. It means beta guy recognizes shabu shabu and does not want to go to shabu shabu when it is in the initial state, Q3, but also it doesn't want to go when he is in Q4, and nor in Q5. So he never wants to. So he knows very well, he knows that he creates some problems in the stomach, and he say, no, thank you, I don't go to shabu shabu. Okay, what will be the final result? the final result will be that the synchronous behavior, in the synchronous behavior, they will not go to the shabu-shabu. This is what I expect. And this is what would happen, for example, if we go from Q1, Q3 again, Q1, Q3, and we ask from Q1, Q3, can I execute beta? Now I should apply this condition. I'm here because now beta belongs to both alphabets. So both guys recognize shabu-shabu. Okay? But the result should be delta A Q1 beta and delta B Q3 beta. But in this case, delta B QB beta does not exist. So this exists. In this case, this does not exist. Okay, so the result now is that we don't go to the shabu-shabu restaurant. Okay, so Q1, Q3 was this one. So this is eliminated. Is it clear? So, what we have understood is that depending on the presence of not or not of an event in an alphabet, we have a totally different behavior of the synchronous composition. Please.
Why is it the state Q2, Q3 going to Q2, Q4 with the transfer function alpha?
Sorry, can you repeat?
Why is the state Q2, Q3 going to Q2, Q4 with the transfer function alpha?
From Q2, Q3.
Q2, Q4.
So Q2, Q3, let's check it. Q2, Q3. So it's the same question as before. I don't go with the label alpha because this automaton cannot transit from Q2 with the alpha. If you are in Q2 and you want to apply alpha, this does not move. So even the couple cannot move. It means that you know what is alpha, but when you are here, you don't want to eat anymore. You know what is pizzeria, but if you are in this state, you don't want to go in a pizzeria. That's the reason. Okay, so this is one of the consequences. Maybe there are other consequences on the rest of the automaton based on this change. Can you figure out what are other changes in the rest of the automaton? What would you do? What other changes would you do in the result, in the synchronous composition, based on this change here?
We should check again whatever is beta transition. To check again if this transition is valid or not.
Okay, perfect. We have to go and check beta transition because that's the change that I introduced. In this specific example, it's also extremely easy to find the solution because basically, since we are finding the synchronous composition, so the fact that we go together, do you think I can accept the event beta in the synchronous composition sooner or later? If you see the automaton D with this alphabet, do you think beta event sooner or later will label some events in the synchronous composition? No. Beta is forbidden. Beta is totally forbidden because if A wants to go, this is forbidden by B. If A doesn't want to go, we have no question at all. So basically, in this particular example, we have to go there and cancel any beta. I will cancel this, now we will cancel this. Okay? So if I try to with sigma A equal to alpha and beta, and sigma A equal to alpha and delta, the result was like this: alpha, beta, delta, delta, beta. On the contrary, if I put sigma B equal to alpha, beta, delta, the result was alpha and delta. So quite different. Okay, so the two results, I computed the accessible part of the automata. It is totally different. Okay, if you remove unreachable states. Okay, so the language of this and the language of this is totally different. Okay, there are some other small consequences like this one. We can compute the language of this synchronous result, right? For example, one string, one of the many strings executed by this automaton is alpha, beta, delta, or alpha, delta, beta, for example. Okay. Can you find these strings in the language of A or in the language of B? No. No, because this is a mixture of events with beta and delta belonging to different alphabets. And so the relationship between the languages of A and B and the languages of language of asynchronous B is not clear. Okay, there is, mathematically there is, but if you try to write it down, it's quite complicated. Okay. On the contrary, now this is an example, but we can you can imagine what happens if we have sigma A equal to sigma B. Okay, you remember the three cases of the delta function that I just answered. Okay. If sigma A is equal to sigma B, basically we will always be in the first row because events belong to both directions. Okay? Can you follow me? So if you are in the first row of the definition of the synchronous composition, okay, you basically have never the situation where you have to mix somehow events from an alphabet and events from another alphabet, because you have just one alphabet, sigma A equal to sigma B. So you have always delta A QA sigma and delta B QB sigma, always like this. And sometimes you have these two elements, sometimes you have not. Okay, as it is the case here. Okay, so this means that all the events that you have, all the arcs that you have in the result are always present in both automata. Okay? Not vice versa. But if they are in the result, they are present in the both automata. Okay? So this basically means that the synchronous composition, when you have sigma A equal to sigma B, is able to extract really the common strings. Okay? That's a strong result of the synchronous composition. Actually, one of the meaning of the synchronous composition is exactly this one. To allow or to forbid an event. So to go with the shabu shabu or not to go, or impose not to go to the shabu shabu. Or in this case, when you simply find the common strings of the two automata through this operation. So in this case, what happens is that the language of A synchronous B is exactly the intersection of the language of A and the language of B, by definition. Okay? Because all these languages are composed exactly by the same event, and the events of the synchronous composition, the strings, of the synchronous composition must necessarily be strings of A and strings of B. Okay, so the synchronous composition is able to extract the synchronous behavior, in this case, exactly the same, the synchronous behavior. Okay, that's again of paramount importance for us because we will exploit this result quite a number of times. Okay. Any specific comment? I have one last comment. Here I call this state Q3. Would it be the same result if I have called this state Q0? Can I call this Q0? And can I call this Q1? And can I call this Q2? The name of the states are not important. Also, Q0 here is a state of B. Q0 here is a state of A. There is no, strictly speaking, any relationship between states of A and states of B. But if I do so, then I get into a mess because I'm not a computer. So if I do Q0 to 0, then sooner or later I get into trouble. So this is why I prefer to change states, but this is not mandatory. Okay? So if you prefer to keep the same names, it's also okay.
It's better to use different names because
Better to use different names
you get
so
confused.
you don't create a problem. Okay? So I think there is no question, so we will meet next time.